Hello again, this is Professor Evans. This video is for EET 1214C, and in this video we are going to go over an introduction to AC circuits. So at the end of this video, our objectives are that you will be able to describe an AC source, that you'll be able to calculate 5 different voltage values or current values related to an AC source. Those are instantaneous voltage, peak-to-peak voltage, RMS voltage, and average voltage. And then in our corresponding lab that goes with this video, you'll learn how to measure the peak-to-peak or RMS value of a sinusoidal voltage in multisim and on the bench. So until now in this course, we've only discussed circuits that contain a voltage source that supplies a constant voltage. These are called DC circuits or direct current circuits. Another type of circuit is called an alternating current circuit, and that contains a voltage or a current source that alternates following the path of a sine wave. This is our symbol for an AC source. So in our previous experiments, we've only ever supplied, say, 12 volts or 5 volts or 2 volts to the circuit, and we knew that that was the only voltage being applied at that time. Now we're going to look at a circuit where the voltage changes with time, and as time goes on, that voltage is going to go up and down like the form of a sine wave. So just to review, a sine wave is periodic. It repeats over and over. This is a quick snapshot of a sine wave showing one period of a sine wave. We have a positive maximum, a negative maximum, and it completes a periodic cycle over and over. So think about a voltage source that is now supplying voltage that starts at 0, increases, decreases, returns to 0, becomes negative, and then returns back to 0. That's what a voltage source does when you have an AC source. Just a reminder that the period of a sine wave is the amount of time it takes to complete one cycle. The amount of time it takes to complete one cycle. That's the period of a sine wave. Period can be measured between any 2 points within a sine wave. For example, from the beginning 0 here, this positive going crossing here, to the next positive going crossing here. That's one period. Period is represented as a unit of time, and we use a capital T to represent period. So on the picture in the right, we have several cycles where we can see the first cycle where it begins and ends, where the second cycle begins and ends, and then where the third cycle begins and ends. I can measure period from several different points. We call measuring period from here to here 0 to 0. From here to here is 0 to 0. From our first positive crossing to our next positive crossing. We can measure from peak to peak. Here's one peak. Here's the next corresponding peak. If I measure the amount of time it takes for the peak to occur, that's also period. We have 0 to 0 right here again. Now these are our negative crossing zeros. When it crosses from the positive y-axis to the negative y-axis, that's a negative crossing 0. So we can measure from that 0 to that 0, or we can measure from negative peak to negative peak. Any 2 corresponding points on the wave can be used to measure period, as long as there are 2 corresponding and consecutive points along the path of the wave. So what happens when we have a circuit with an AC signal? Well, let's take a look. Let's say that we have the circuit shown right here, one resistor with an AC source. That source is going to deliver voltage that changes with time. And when the voltage is positive, the current that flows from the source and around the circuit is going to flow in a clockwise direction. When we get to the negative part of the sine peak, the current changes direction, and now it flows the other way. So as the current direction changes, the polarity of this resistor also will reverse, and that leads to some different characteristics that we don't see in a DC circuit. So as the voltage changes, as long as it's positive, it's going this way, and the voltage will increase, then decrease, become 0, and then become negative. And at that point where the voltage becomes negative, the direction of the current flow changes. Now it's going counterclockwise. And again, that means the polarity of your resistors are going to continue to flip-flop as long as this sine wave continues to have both positive and negative alternations. So, as we discussed, period is the time it takes to complete one cycle. The other characteristic we have with the sine wave is called frequency. Frequency is the number of cycles a sine wave completes in 1 second. So frequency is a rate, cycles per second. It is measured in hertz, Hz for short, hertz. Frequency and period are reciprocal relationships of one another. So if you know one, you can find the other. Frequency is 1 divided by period, or period is 1 divided by frequency. So we have 2 sine waves on the screen now. Let's look at the frequency of the one on the left. The amount of time that has passed is 1 second. Let's look at how many cycles happened in that 1 second. We have 1 cycle, 2 cycle. 2 cycles per second. In the same second that passes, the circuit on the right is showing 1, 2, 3, 4 cycles per second. So this is an example of a higher frequency where you have more cycles happening over the same amount of time compared to a circuit with a lower frequency, less cycles over the same amount of time. So I want you to take a look at the 2 waves on the screen and tell me what is the period and the frequency of each wave below. So take a few minutes to pause this video and see if you can figure that out on your own, and when you're ready, come back to see the answers. So with the one on the left, we have 1, 2, 3 cycles per second. So our frequency would be 3 hertz. Our period is then going to be 1 divided by 3, or 333 milliseconds, meaning it takes 333, or about 0.3 seconds, for 1 full cycle to happen, which makes sense. If I can get 3 cycles in 1 second, then it would take a third of that time to get just 1 cycle. For the one on the right, we have 1, 2, 3, 4, 5 cycles. 5 cycles in 1 second. So that means our frequency is 5 hertz, or 5 cycles per second, meaning our period is then 1 over 5, or 200 milliseconds. So if the frequency is larger, the period is smaller. Compare the one on the left, the one on the right. The one on the left has a lower frequency, which means it has a longer period. That 1 cycle takes longer to occur. Higher frequencies means that 1 cycle occurs in a much faster amount of time. So there are 5 ways to express the amplitude of a sine wave. One of our first values that we're going to use to express a sine wave is called the instantaneous value. At any point in time, what is the voltage or current of a sine wave? Typically, instantaneous values are represented with lowercase letters, lowercase v for voltage or lowercase I for current. So in this example, let's say that I want to know the exact amount of voltage that is happening at this moment in time. I'd be looking at this value of the wave right here in order to know that instantaneous value. We also have what's called a peak value, and that is the value of the voltage or current, because you can have a sine wave that represents either voltage or current. It's the value of that sine wave at its most highest or most negative lowest point. So our peak value is the level of voltage or current you have at the highest peak or the lowest peak. And that's represented with V subscript P or I subscript P. Peak value, your highest or lowest point. Then we have peak to peak value, which is the distance from your tallest point, to your lowest point. Peak to peak value. And that's your voltage or current from each positive to each negative peak, each positive to each negative peak going in a vertical direction. So the distance from your positive peak to your negative peak is your peak to peak value. The peak to peak value is always going to be twice your peak value. If I know the peak value, I know peak to peak is just twice that. The next value we have is called the RMS, or root mean square value. Your RMS value is 0.707 times your peak value. So that's a formula that you can memorize. RMS value, the RMS value is equal to the value of the direct current or voltage that would produce the same average power dissipation. Meaning, if I were to connect this signal to this AC signal to a resistor, and I wanted to connect an equivalent DC source to the same resistor and get the same power, what is the approximate value of that DC source I would have to use? That's your RMS, or root mean square value. And again, it's generally calculated as 0.707 times your peak value. And we can see that it's 0.707. And that's a constant value. It's not changing. It's a constant value. And then our last value is the average value. Now, if you've taken calculus, the average value is an integral. It's the area under half of this sine wave. If you haven't taken calculus, think about calculating the area of a square or a rectangle. In the same way, if we could calculate the area underneath the shape, that represents the average value. Our formula for average value is twice the peak value divided by pi, which comes out to be approximately 0.637 times your peak value. So these are our 5 different values that we might use to express different characteristics of an AC wave. So let's practice using those different characteristics. You have an example on the screen. You have a voltage wave changing with time. The time is in milliseconds. Try to answer each of these questions using the information that we just discussed. So starting with the first one, what is the instantaneous voltage at t equals 4 milliseconds? So at 4 milliseconds, I'm going to go right here. I'm going to try to interpret this value, and it's about 150 volts. The peak voltage also occurs right at that same point, about 150 volts, maybe 151 if you're just reading it from the chart. The peak-to-peak voltage is going to be twice your peak voltage. So 150 times 2, 300 volts. Our RMS voltage is going to be 0.707 times your peak. So that's 0.707 times 150, and you get 106.05 volts. And then your average voltage is 0.637 times your peak, 95.49 volts. Then the last 2 questions are, what are the frequency and what is the period? So you might have to try to figure out, well, which one can I find first, frequency or period? So remember, frequency is cycles per second. Can I figure out how many cycles happen in 1 second? That's not super apparent. Well, let's think about the definition of period. Period is the time it takes for 1 cycle. Can I estimate the time it took for 1 cycle? That's a lot easier. I can see that the time it took for 1 cycle is about 17 milliseconds. So let's start by saying the period is 17 milliseconds. And then I can use that to find the frequency by saying 1 divided by period equals frequency. So we get a frequency of about 58.82 hertz. That's how many cycles would happen in 1 second. Here's a second example for you to try on your own. Make sure you understand how to use these various calculations to apply to a sine wave. So take a minute, hit pause, and then come back for the solutions. All right, so when you're ready, here's the instantaneous current at 0.6 seconds. It's about negative 0.75 amps. Negative 0.75. If I go down here, come across. The peak current, 1 amp. Peak to peak current would be 2 amps. RMS current would be 0.707 amps. Average current, 0.637 amps. With this one here, I can see the period is 1 second. 1 second for a period. Which means my frequency is also 1 hertz, 1 cycle per second. This is how we use those different values to interpret information from a sine wave. Lastly, we're going to look at how a sine wave is displayed on an oscilloscope. So on the right, we have a picture of a wave that is taken from an oscilloscope. We have our wave here. We can see it completes 1 period. And we're going to use this information at the bottom to answer these questions. So at the bottom, I have two indications or measurements here. This number right here tells me about the y-axis. It tells me that every box going up vertically is represented by 0.2 volts. This tells me about the x-axis. This tells me that as time goes on, time is always going to be on our x-axis. As time goes on, each box horizontally represents a time of 50 milliseconds. So knowing that each box represents 50 milliseconds horizontally and 0.2 volts vertically, we're now going to answer these questions. So starting with the peak value, I can see that the peak value is 1, 2, 3 squares high, and each square is 0.2 volts. So 3 times 0.2, 0.6 volts or 600 millivolts. Again, voltage goes vertically, time goes horizontally. So next question is, what is the period? The period is how long it takes for one cycle. Well, I can see that one cycle is represented on the screen. Let's estimate how many boxes that covers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 boxes at 50 milliseconds per box. So I'm going to do 10 boxes, or we call these divisions, 10 divisions, times 50 milliseconds per each division or per each box. So you have 500 milliseconds is your period. Then I can use that to find the frequency, 2 hertz. Remember, we're just taking the reciprocal. Then I can calculate the RMS voltage by saying 0.707 times the peak that I calculated earlier. And I can do the same with average by doing 0.637 times the peak we calculated earlier. So this is how we can read an oscilloscope. In our lab, we're going to learn how to display an AC signal on the scope and take measurements. And it's important to know how the divisions are set up. So going horizontally, the divisions are time-based. And so you're going to look for how your scale is set up. In this case, the scale is set up for each division to be 50 milliseconds of time. And then our voltage divisions, 0.2 volts per division going vertically. This is how we read an oscilloscope to determine the data that the scope is showing us for an AC signal. And that's it for this video. If you have questions, as usual, please email me, send me a Canvas message, or comment on this video, and I will send a response.